So again, Andrei Okounkov will be speaking, and again, someone doesn't need any introduction.
Thanks, Mario, for the introduction. Thanks for nothing. Yeah. No, it's really very nice to be back here. I apologize for not being able to come earlier due to my teaching obligations. So I'm going to talk about, Nikita commissioned to talk about stable envelopes in K-theory and applications. And the notion of stable envelopes and the generalization in K-theory, this is some long joint project I have with Davesh Malik. But in applications, I'm not sure how much time I'll have to describe the application, but the main application is to something that some joint work we've been doing with Nikita. But it also, I don't know. It's kind of it's going to say, well, there's certainly related work by my students, Andrei Smirnov, Daniel Schenfeld. And it's also going to say a lot of some projects I've, some work with related work by other people, but so in particular some work we've been doing with Mina and Najik. So I'll review what the notion of stable envelopes was in cohomology. So let X be, say be a equivariety, an Nakajima equivariety. E.g., you can take it to be, the most very interesting example is already the cotangent bundle to Gerstein. And this, no, I think it's on, yeah. And this, of course, you can generalize in many different ways. You can make it to be, mathematicians like to think about this equivariant symplectic resolutions. In Nikita's and Samson theory, that embeds into larger worlds of this vacua. And what the conference is about, and this Suzy gauge theory that and what's the main statement that not the main statement. The main statement for us, what Nikita and Samson say, is that if I look at the cohomology of X, and there'll be some group acting on X, say here is I have on the cotangent bundle, I have the reaction of the group with GLN, which acts on the base, and C star that scales the cotangent fibers. I look at this of X, or maybe K theory. So we'll start with cohomology and then talk about K theory. Then this is the Hilbert space of some quantum. This is a space, Hilbert space. Space of some quantum integral system. That is, and the symmetry of this system is, well, in this case, is some Yangian of some suitable Lie algebra associated to X, and well, we'll just this G has nothing to do with this G, so maybe keep Gx here. And or in this case, it's the UQ, which again I'll denote UH bar since it's a different Q of the loops. That's the algebra of symmetries, and the corresponding Baxter subalgebras in here and in here, that parametrized by Baxter subalgebras that depend on a choice of an element, of some element we'll denote Q now, because that's the Q, the quantum cohomology Q. It's a vector. It's not. This is an element in the exponentiated Cartan subalgebra of this Lie algebra X. So these are the algebras. These are the algebras of quantum multiplication. And in one, so it's the ordinary quantum multiplication. In the other case, the K-theoretic quantum multiplication. So I'm not going to describe the mathematical progress towards explaining this. I'm just going to say that this is very easy to see in the example. In this example, in which case this is the ordinary Yangian action and UQ action that Nakajima, or maybe in this case people before Nakajima probably constructed. And so what I was going to say is that if it's easy in this, if this parameter goes to 0, then this becomes algebra for ordinary classical multiplication and cohomology. Both these spaces are just rings. I mean, naturally, you can multiply cohomology class, you can multiply the K-theory classes, and this becomes, and this commuting algebras degenerate to just algebras of multiplication here. And in the case, well, let's say, let's make an assumption that the maximal torus. So let's make a simplifying assumption, which it's not necessary, but let's make it for the pedagogical purposes. Let's imagine that the maximal torus. I take the maximal torus T in G. Its fixed points are isolated, which is the case for the Grassmannian. Then as Q goes to 0, this becomes, as I said, you get the operators of just multiplication, cohomology, or K-theory, and this is certainly diagonalized in the fixed points. Fixed points. They diagonalize multiplication, because in fixed points the multiplication is just delta functions. They're eigen. Therefore, the fixed points. For Grassmannian, the fixed points are the coordinate subspace. If I choose the standard maximal torus in JLN, the diagonal torus, that this is going to be coordinate subspaces, and there'll be n choose k of them, and they just they diagonalize the. These are the beta eigen vectors as at Q equals 0. So this is the basis, which is very easy to describe in this Yangian terms. And the question is, well, how about what is something like this? Yeah. So and the question is, how do I describe what is this? How do I describe the original basis, the original spin basis? So the question is. So a question for Grassmannian in a more general situation, the original spin basis.
You want to construct actually the spin in each lattice point.
Yeah. So it's a very traditional. So if I have identification of my space with the Hilbert space in this case of XXX chain, and I have a basis. I can characterize the basis of fixed points, but in terms of Yangians, and I need now reconstruct the spin basis. in cohomology or K-theory, that's equals question mark.
I think it was done by my work is Nazarov on Gilfen's basis. Isn't it?
What?
Well, so on Gilfen's certain basis for Youngians. You know this work and it.
Yeah, the question is how to describe this in general geometric terms applicable to general quiver variety, or how to describe how to uncover the geometric meaning behind your old formulas. I mean, just you're asking the transition. You're asking the transition matrix for particular quiver varieties. I mean that's known, but to understand what it means geometrically, how to do it for some varieties, you know, to give you a general quiver variety, you and Nazarov haven't written a paper about that. So that's and then the answer is, and so this is you know this is, I'm just by way of introducing this concept, and the answer is given by this under the assumption that this is a finite set, can be defined in general, but I'm taking this pedagogical simplifying assumption. So this is the basis of, these are the stable envelopes of fixed points. And I'll first review what they mean in cohomology, how you construct them in cohomology. So if I have so to define them, the first thing you need is you look at the spin chain. There's obviously some ordering. So the abstract notion of an ordering is you need to pick so if you have in my maximal torus, I consider the subtorus. This is a subtorus that preserves the symplectic form. So this would be the, in this example, this would be just the all diagonal matrices, 1 through an. And in the Lie algebra of this torus, I have to pick a generic. I have to pick a direction. And here I pick a direction. And so this means there will be some, in fact, this Lie algebra. This will have a certain chamber decomposition, and if as long as I pick this direction in some away from certain walls, it's not going to depend on which direction I pick. So in other words, what I'm picking is really I'm picking some cone in the Lie algebra. And the walls is where this is where the fixed loci. The walls are defined by, this is where the fixed loci jump. So the walls are those elements of the Lie algebra that have more fixed points than usual. So in this case, it would be if two of the eyes are equal, then there's a wall. So once you define this, then for every fixed point you have associated attracting and repelling manifold. So maybe you have a fixed point P, and I look at the action, how my Lie algebra element acts in the tangent direction to this. Well, there will be some manifold to which this action contracts. So maybe vector field goes something like this. And there will be some directions which repel. So this preserves the symplectic form. So there'll be as many repelling as attracting directions. So there'll be some repelling directions here. And I can take the attracting manifold, the entire manifold. There's some kind of attracting manifold, which is which is known for say, for Grassmannian, the attracting manifold. This is a Schubert cell. And in general, generalization of Schubert cell. And which we denote this, which we denote attracting of P. And the definition of a stable envelope in cohomology is that the stable envelope corresponding to my choice, there's a choice of a chamber here, maybe we'll call it C, in cohomology. This is the class of the attracting manifold of P. So it is Schubert, in Schubert cell, or rather, in Grassmannian will be a Schubert cell, in the cotangent will be the co-normal. In the cotangent bundle, it's going to be the co-normal. Plus, so this is not such a good definition. So this is, you have to add, what you have to add is this the, you consider the closure of the Schubert cell, it's going to contain other fixed points. Right, so this is obviously. Right, so it'll be some other fixed point, maybe call it, maybe we'll call it prime. That contain, they're not in the attracting manifold, but they're in its closure. So if we say that if P prime belongs to the closure, let's say this is the closure, attracting P, and we say that P prime is less or equal than P, plus a combination with some coefficients, maybe call it M, P, so sum over P less than P, with some coefficients M, P, P prime, which are integer coefficients, of the classes of attracting manifold in P prime. And that because I'm saying I start with a fixed point. I could look at this attracting manifold, it's some kind of Schubert cell. I take its closure, and instead of taking, that's a class in cohomology, and instead of just taking as it is, I add a certain linear combination of smaller Schubert cells, so that to satisfy a certain condition. And the condition is, so the main condition. So these coefficients are determined from the following condition. So maybe what's the that I take this class and evaluate it, restrict it to any fixed point below or any other fixed point. Restricted to P prime. What I'm going to get? I get a restriction of a covariant cohomology class to a point. So I get an element. So this is an element. This is an element in the covariant cohomology, or in this case, it's an element in the covariant cohomology of a point. So it's a polynomial in the covariant parameters. So maybe I'll write it like this. And the condition is that, so there was a cohomology class on the space. We restrict it to a point. We get an element of covariant cohomology of a point. So it's a polynomial in the covariant parameters. And the condition of this polynomial is that its degree along the parameters in the Lie algebra of A, let's call this A. Like this, its degree in A is less than the dimension of repelling manifold at P prime. And they claim that there exists unique choice of this constant here that satisfies this, and then and that this is the basis in which this is the spin basis, and you somehow see it very explicitly that this was the this definition involved a choice of this vector. For example, for Grassmannian, it's going to involve a choice of ordering of lattice sites, and so then you can, and so then if instead you choose a different one, if instead of this vector you choose a different direction, let's say this one, then this construction will change, but it will change precisely by the transition from one chamber to another, or reordering of the lattice site will force a change in the basis, and that change will be given by a certain R matrix. So if I think of the
Would you say why that's a natural condition to impose?
Yeah, because this is the degree. If you take just by itself one of these classes, it will have this degree. So if you want to fix this polynomial uniquely, you probably may want to cancel the top degree term. But it's a very useful condition. It's somehow this condition gets used over and over again somehow. But basically it says that if you, for example, how do I know that adding, if I take one more unit of some of these guys, why do I violate this condition? Because this has the precise degree equal to this, and this would be violated at that point. And so what I'm saying is that what I've really constructed for you. I took the cohomology of the fixed locus and constructed a map to the cohomology, to the equivalent cohomology of the whole variety that depended on the choice of a chamber. I can now take a different chamber and go to the same space. Now these spaces are the same, and so if this has to be a map here that makes this diagram commute, and what this map is the R matrix. It really still is the R matrix. If you think of the Grassmannian as corresponding to spin chain, that really the SL2R matrix you just don't announce there. And if for any quiver variety of finite type, you'll find the corresponding the corresponding R matrix from the work of Fadeev's school. But if you go to quivers beyond the finite type, you'll find new R matrices, which are not, as far as I know, they're not, somehow don't have names. All right?
So this is a polynomial on the Lie algebra of T, but you only care about its degree as well.
Exactly, you only care about this degree in A. So that's a very kind of important condition. More questions before I go to K-theory?
Where's Q?
Q? No, this is purely classical, nothing quantum yet. This definition, the point of view that these are the purely classical things. Like if you think of the Baxter subalgebra, that has a parameter. That's the quantum parameter. But the R matrices themselves, they don't have that parameter. They just.
Can you explain Baxter subalgebra?
I don't know. I think it's the subalgebra. I don't know how to go. It's you take the trace. You take the trace over the auxiliary space of some operator Q tensor 1 R01.
So the commutative.
Yeah, that's I don't know. The algebra of transfer matrices, yeah. Sorry, Rashid taught me to call this Baxter subalgebra. You can ask Rashid. Yeah, I apologize if I offended anybody who's invented this before Baxter.
You just delegated it to someone.
Yeah, exactly. So Rishitichin is, yeah. I can give, yeah, what? Rishitichin, yeah. If anybody can complain, we can call Rishitichin now. So, yeah. Yeah, yeah.
It is recorded.
It is recorded, okay. Yeah, I mean, did I say anything controversial yet?
Instead of you, we should take him to the corner.
Yeah, right. Anyway, so I don't think it's controversial. So, so anyway, so that's the construction. Okay. I mean, I don't know if you don't think in terms of covariant cohomology, maybe you find it slightly complicated. But maybe the good example to do is the cotangent bundle of projective space. Then the Schubert cell are just subspaces of various dimension. And here, this stable envelope, if you take this, the coefficients are, well, this is 1, and then you take the next one, this coefficient 1. And that's it. That's the formula. Each stable envelope sum of 2 terms. And all the coefficients are 1. And you can do this example.
What determines the coefficient?
This condition that the degree of the restriction, you restrict a class to a fixed point, you get the polynomial covariant variables. And the degree of this thing has to be less than the codimension. I mean, the codimension of an unstable part. So there's attracting manifold and there's repelling manifold, and it's the dimension of the repelling manifold that bounds the.
Maybe we need to know how to restrict the class of the attracting.
I know this you cannot learn in finite Yeah, I don't know. It's just very simple. Covariant cohomology is much simpler than ordinary cohomology, but I don't think I can explain it within the talk. Yeah. So. Okay. So, but in K-theory it's easier. In K-theory it means you have an equivariant bundle, and it has you can take its resolution, its restriction of an equivariant vector bundle to a point is just its fiber at the point. It's a very simple operation. Everything can, if you have a smooth manifold, everything can be resolved by equivariant bundles, and then you just take the fibers at points. So that's so when we go to K-theory, it'll be easier. Okay. Okay. Now, so I think it's time to go to K-theory, and the definition is this. So you just everything as before, but now, of course, it's not a cohomology class; it's a sheaf. And it's a sheaf supported. So now this thing is a sheaf supported. So it means this guy is supported. Is maybe I'll write like this, is equal, you take the structure sheaf of the attracting manifold, or plus a sheaf on the union of the attracting manifolds less than P. So, I mean, every time you see a manifold in cohomology, in K-theory you should think the structure sheaf. In fact, for the future, maybe it's better. It's best to have an option of twist by line bundle here. And if you see a manifold, then if you see a cohomology if you see a manifold, maybe like with multiplicity 1, then maybe you should think that in K-theory it corresponds to a line bundle over D-brane. Yeah, right, exactly. Okay. Right. It is. I mean, it is D-brane. Yeah. Yeah. I mean, it really is D-brane. So and so then restricting restricting K-theory class to to a point, well, that's an easy operation. As I said, you have any sheaf you can resolve by locally free sheaves, and restricting locally free sheaf, you just compute the fiber at the point. But then the restriction now says this restriction now what is it? It's now representation. This is now representation. This thing is now representation.
Virtual.
Yeah, virtual. Representation of my torus, of T, and then also of the subtorus. Previously, it was a representation of a torus, but we only cared about its, what the weights here. And now, that is to say, what's a representation of a torus? It means it's Laurent polynomial with integer coefficients. And so then, if you have a degree of Laurent polynomial with the notion of degree of a Laurent polynomial is the notion of Newton polytope. Right, so maybe I'll write Newton. But if I have a Laurent polynomial, let's say in two variables, like degree of x plus y plus 1 over xy, then I should think of this as this. That's a very familiar picture. I should draw on the lattice the exponents, and I should take the convex hull of the exponents that appear. I think it's well known fact that the right analog of degree for Laurent polynomial is its Newton polytope. And so this then has to be smaller than the Newton polytope of some of what? So this has to be smaller than the Newton polytope of previously this bound was coming from the fact that if we were to add a copy of the attracting manifold, this will spoil our dimension estimate. So we'll just take the structure sheaves of the attracting manifold. Because you see this somehow, if you take the for the manifold, then restriction cohomology has to do with the normal bundle. It's a product of normal weights. So the repelling manifold. I mean, this is by Kazul. This is equal to the exterior algebra, I mean, with some kind of minus sign of the dual of the repelling. With the dual of the repelling, I mean, this is if you're to resolve a submanifold, you have to take the Kazul complex for the dual of the normal bundle. And so what's this Kazul complex going to look? I mean, in other words, if you take the weights, if you take the unstable weights to column, I don't know, W1, W whatever, Wi, then this expression will have this representation of a torus will be a product of 1 minus Wi inverse. And so this is what it is. It's an image in some kind of bigger space. You have a cube. Because if this were all linearly independent, the Newton polytope of this would be cube, and in that cube you're projecting it to you project this to the Lie algebra to the dual of the. So this, the color thing is not so easily replaceable. So it's going to be some kind of polytope like this. Inside all of these weights, W are all negative. Their W inverse are all positive. So this all point in the positive direction in the torus. And you're going to get something like this. This is my 0. And smaller means that, what do you think is a polytope that's smaller than this one? It means, well, let's denote this polytope delta of P prime, the Newton polytope of this expression. And smaller means I want smaller. So it means contained in delta P prime minus the maximum vertex. So for all these were positive, these were all Wi inverse, were all positive things, and there'll be the maximal one, which is the product of Wi inverse, and you remove this one. You have to take some kind of canonical polytope that's smaller than this. It has two canonical vertices, this minimal and maximal. You can remove one or you can remove the other. They're related by duality, but you remove one vertex. Suppose you have two functions with the same Newton polygon.
The degree being strictly less?
Exactly. There's some kind of, this is some kind of largest.
Including, so it could coincide.
Well, it could be strictly inside, but it's somehow just at least included. It's inside, and this vertex is missing. Because if you have two functions with the same Newton polytope, you can kill one coefficient, and this is the coefficient you kill. And so then at this point you can ask the questions why you took the maximal, not the minimal. In this expansion, there are two canonical terms, the one and the maximal term. I took the maximal and took the minimum. And also, everybody knows that the Newton polytopes are really defined only up to translation. Really, somehow, this is the more canonical way to think about it. If you multiply by Newton polytope associated with the function of the torus, if you multiply by invertible thing, you just translate Newton polytope. And as I said, they're going from maximal to minimal. That's like duality. You can define the stable and the dual stable envelope. But translation is more interesting. And so this is how we're going to address the translation part. So translation. Maybe we may tweak this definition. The definition by requiring the Newton polytope of stop P restricted to P prime to be included in this delta P prime minus maximal vertex plus some fixed lattice vector, some kind of shift which depends on P and P prime. This is an element in the H. It's a character of the torus. And so what are the good shifts? So for example, e.g., if we conjugate, we can take this whole construction, we can conjugate stop by a line bundle. Meaning, if in K-theory you have all these automorphisms tensoric with a line bundle, You can take this step as a map on K-theories. You can just conjugate. So what would be the result of this? This means if I conjugate by a line bundle, I'm picking an extra weight. This S would be the weight. Oh, I'll just write L restricted to P prime minus L restricted to P. For line bundle I restrict to a fixed point, it's going to be a character of the. It's going to give me a character of the Torosian element in here. So this is, I can do this. Now this some kind of the next observation about it is this makes sense not for integral line bundles, but also for fractional line bundles. Because what I can do is I can, say take the integer part here, and then this makes sense not for integral line bundle, but for fractional line bundle. That is in peak x, peak gx, and the q. This is extremely reminiscent of higher dimensional algebraic geometry, I must say. So, and then in fact, there has to be some kind of way of in saying that all these fractional line bundles correspond to different birational models of the quantization of x. This really must be a way of saying this, but it's a. Maybe I'm not prepared to make a concrete statement in this particular talk. So now the conclusion of this, what we really got is a map what one really has is not just a map parameterizes. So one gets a map between the K-theory of the fixed locus going to the K-theory of the whole thing. This K-theoretic stop, but now it depends on the chamber and on the fractional line bundle. So now instead of just having, so this C is as before C is a cone in the Lie algebra of A. C was a cone in the Lie algebra of A. And L, again, if I change L a little bit, it's not going to affect this formula. So L corresponds to some alcove in the this is my peak x tends to q, and L sits in some kind of alcove here. So the peak x tensor q is going to be also partitioned into chambers, and this would be the chambers now will be bounded, and this whole map depends now on this entire data. So in particular, you have more richer set of R matrices corresponding to crossing walls in this kind of richer space. Now and where this comes in? This has a certain. So in other words, you see a construction which incorporates two dual things. It incorporates the Lie algebra. I'll explain why it's dual. So why the Lie algebra of the symplectic torus and the APK, so one application of this is the following. So I know how much I can say just in 15 minutes, but so Nikita and I were thinking about the following issue. Suppose you consider the following setup. Now X is going to be. I apologize. I'll use X for something else now. Or you want to call it something else, the X, or it will be confusing. What do we call XX now? What's a good name for Calabi-Yau fivefold?
Let's call it Z.
No, Z is the partition function. Y? No, Y is the fixed locus. M. Okay, let's do it M. So let's consider the following situation. When I take the M, it will be Calabi-Yau of all 5. I mean, that's not so good, but it's okay. And such that a torus C star acts on M, preserving the 5 form, and such that the fixed locus, which call it Y, is 3-dimensional. Dimension of this, which is the fixed locus. So then there's a quite precise conjecture about how to compute the index, the M theory index, on a manifold which fibers in M over circle, in terms of some specific DT theory on Y, K-theoretic. That DT, K-theoretic. And so in particular, for any Y could be, if Y is itself a toric variety, so if Y is itself a toric variety, then I'll look at my notes. I have it somehow coherent. So if Y is toric, threefold, that then the K-theoretic DT can be computed in familiar terms. I don't know if you've I suppose you've seen it. If you have looked the toric diagram of Y, and you place some kind of pile of boxes here that so you place partitions on every edge, and you place a pile of boxes at each corner, and there's some weight associated to that, which is a K-theoretic analog of the old homological weight. And anyway, this can be computed in terms of this trivalent K-theoretic vertex. Which is when you fix the 3 partition, you consider all possible boxes, etc. So if additionally, a Y is itself Calabi-Yau, then it can be seen that this result is in fact independent. This K-theoretic computation means that it's a virtual representation of in this case a 3-dimensional torus, but in fact it's independent of the variables in the Calabi-Yau subtorus. This if additional then the partition function, then z dt k y is independent of the variables in this C2 Cy checksum. It's the one that preserves the Calabi-Yau form, the Calabi-Yau 3 form. And so in particular, what you can do, you can take a limit. You can simplify your life by taking this variables to infinity. Taking these variables to infinity, this is already this plane of the board is the dual of the Lie algebra of this Calabi-Yau torus. That's the plane of the board right now. And picking in some direction and sending variables to infinity, that's the same thing as picking a direction, somehow dual thing. Picking a direction here, and it's a kind of co-orientation. I'm just drawing a covector. Covector has a 0 somewhere, and it's also again positive or negative. And so And so in this trivalent vertex, what you can do is you can take equivariant parameters to infinity, and what? And simplify your life therefore. So there's some more basic object. If you take the equivariant parameters to infinity, there's some more basic object at this, with some kind of, you choose a slope, send your variable to infinity, you get this, what we call the index vertex at a given slope. And let's see how this index vertex can be computed. So the first step is to trade this three-leg geometry for a different three-leg geometry, which contains the same information. Namely, instead of the geometry over there, I'm going to choose the geometry where you have a A2 surface. So I place 3 precisions here. Something like this. And then I have a pile of boxes that cancel these 3 precisions. But there's empty on these 2 sides. And I get 2 additional parameters here, which have to do that I get a Kähler parameter A1 and maybe a Kähler parameter A2 for these 2 compiled curves. A slightly better object than the plain trivalent vertex. And so what this thing is this thing is how do you call this K-theoretic linear sigma model type of partition function? I don't know. Let's say we'll write it. This is an integral over K-theoretic quasi-maps. It's like a K-theoretic. Yeah, well, there's so quantum K-theory. Yeah, that's right. So, but quantum K-theory can be ambiguous. You can think different computification. K-theoretic quasi-maps to the Hilbert scheme of the A2 surface.
So this is a three-dimensional specification.
Okay. 3D Suzy. And from I didn't say, but in fact you can I didn't say, but in fact you can also consider you can also further generalize it. Or instead of Hilbert scheme, you can study rank R sheaves on the same thing. Rank R sheaves. More generally, you can study quasi-map to the space of rank R sheaves on. Sheaves on A n minus 1. And from this, the way, from various other arguments, but in particular how we reduce this, how we make this transition from M theory to DT, it's kind of clear that there is a more or less relation between Z, whatever, all that, of you study rank R sheaves on an minus 1 surface, that's identical to Z, same thing, rank n sheaves over AR minus 1 surface. with the identification of parameters is that, like in this case, this is like familiar geometric engineering somehow souped up to this, to the quantum K-theory level, where for example these scalar parameters A's become equivalent parameters on the other side. So the scalar is exchanged. And in fact, it's an instance of a more general philosophy by which you can take variety X as before. You studied this 3D SUSY gauge theory on that, and this you can replace by the same thing for some kind of Langlands or symplectic dual. And that's of course Langlands duality is the Langlands duality would be when this actual, for example, X could be the T star of G mod B, and then if you take the T star of G Langlands. And so this notion is discussed by in many places. For example, there's certainly very extended discussion in the work of for example, Licata, Proudfoot, Webster, and Braden about how certain symplectic resolutions are dual to some other symplectic resolution. And so, but the main gist of the story is the exchange of scalar equivalent parameters. And so let's now see is what this limit procedure is going to do. To so if we're only interested in the index vertex, we can ask what this limit procedure is going to do we take the limit to the index vertex. So we take the index vertex for X. That's a limit when I take the equivalent parameters on one side and I make them ultra-equivalent. Means this would be this means on the Langlands dual side I'm killing the scalar parameters. So the quantum computation goes away. And I'm left with just the classical computation. Okay, so that clear? Something classical for X Langlands dual. And where is that? What this thing is going to be? Well, it's going to be just more or less if I take this picture with three partitions, this three partition constitute a point in the fixed locus of my space X. Right? So the arguments here were the points, and this incidentally the fixed loci for this and Langlands are the same. It's part of Langlands duality somehow. And so what this thing is, you have to take that same fixed point. So maybe I was just saying. And that's, as I said, I don't have time to do justice to this discussion, but I urge you to look at the work of Braden. There's some other discussions of this, but I think the particularly explicit is in the work of, I think, Braden, Licata, Proudfoot, Webster, if I remember correctly. If I don't, I apologize, but there's certainly and what this thing is, it will have to depends on the slope, and the slope was a parameter in the Calabi-Yau torus for, this is in the Lie algebra, this is a parameter in the, what was the slope? The slope was a parameter in the Calabi-Yau torus for in one bigger dimension. Therefore, it's a parameter. It's just really a parameter. Slope is really a parameter in this A. This is the slope. It's just really a point. It's not a direction. It's a point in here. And that point that space here is identified, well, say if we take it over Q, it's identified to pick XL tensor Q. And so therefore here we're going to get this stable envelope corresponding to that slope S of this point P. And that's classical computation. It's more or less the Euler characteristic of this. So in other words, I killed equivalent primes on one side, and therefore killed the scalar parameters on the other. But the remaining scalar parameters are one, and equivalent on the other live, and that's just a classical computation on the other side, and that's the result. So in particular, if I take two index vertices. We take two index vertices here and ask for its braiding, namely how I'm going to analytically continue this to the ranges where this is expansion in some particular range of scalar parameters. But I can ask, well, how to analytically continue to some other range of recurrent parameters. Then what I'll have to do is I'll have to know how this basis changes under the change of under the corresponding change. And that's exactly, so this means scalar parameters here will be equivalent parameters on the other side. It would be just exactly, this would be the framing, this would be the constant gauge transformation on rank 3 instantons. And so that would be exactly the R matrix that Smirnov computed. I alluded at the beginning to the work of Andrei Smirnov, who's a student at Columbia, and he computed this for this modular space of instantons. He computed the corresponding.
I lost the picture about half an hour ago, in fact, and
What? That's not from.
I think this is from a
no, but I've been listening, but it's been difficult to listen because of the noise of the plates and the other things.
I see.
But I'm getting the gist of it, yeah.
I see.
Yeah, we don't want. We're not supposed to hear that. This is my congratulations.
Yeah.
Okay.
So, all right, that means the. Okay, Nigel agrees with me. And what I was going to say is that there's some project which, Well, anyway, so look, that's just the subject's too long and the talk is already 5 minutes over time. But so maybe I'll just. Bye. Well, I'm saying if you're looking for some kind of Yangian constraints for this index vertex, that's how you get them, because you see that this is like the constraint from braiding this thing is just going to come from the change of this as you cross the walls, and that's we understand pretty well this is going to be a Yangian type of thing. So, not the Yangian UQ of GL1 hat constraints for this. It's going to come from that. I don't know. Maybe I'll stop here. I apologize. I apologize for going over that.
Questions?
Mm-hmm.
Could you explain why this vertex computation is the same as computation on rank 3 sheaves? So you have 3 partitions.
That one?
No. The vertex there is the same as computation of.
No. This is the vertex. But in principle, in principle, Downton and Thomas series defined in higher rank too. There could be also a higher rank analog of that, but it's not. This particular vertex is not equal to higher rank. That's just a vertex. I've somehow drawn a picture of vertex in rank 1. It also exists a higher rank vertex, which in this case would be instead of 3 partitions, you have 3 times R partitions. On each leg, you have R partitions. And then by this duality, which we describe here, that's going to be related to the other way around. You have also 3 R partitions, but not viewed as shifts of rank R on A2 surface, but rather shifts of rank 3 on AR minus 1 surface. Yeah.
Any relation to Y systems?
Yeah. I just learned the definition of Y system in the break, so.
Can you say something about generalization of that AN-AR duality to arbitrary pair of two AD groups? Duality?
So this AD, it's not so clear because there's no smooth moduli space for D instantons on a surface. So this is an issue which somehow one should be able to say it in some kind of, one should be able to somehow define for singular spaces, but that's certainly not a question for me. I mean, when you had Nakajima here, you should have asked him. So how to define this if the space is singular? Yeah. So certainly the short answer there is an issue in the way that, for example, in cohomology you can get away with intersection cohomology. But there's, as far as I mean, Ginsburg offered a lot of money for intersection K-theory a long time ago, and that's somehow still, the price hasn't been claimed. Yeah. So it's how to deal with singular spaces, I don't know. But in principle, yeah, so in principle there's a general notion what it means for two spaces to be symplectically dual. And I certainly expect, and if you take two surfaces, like A surface and D surface, and you think of this, M theory of, you think of some kind of, like vibration by, A surface cross D surface over, some kind of curve, then you should be getting like on one side D instantons on A, on the other A instantons on D. But that's okay space. But yes, this space is I'm not sure what to say about it.